So waves are everywhere in our lives. Every ripple in a pool, every earthquake, every sound that you hear when you go running, the way the shock travels up your body from the impact of your feet on the ground is by waves in your bones. Fundamentally, quantum field theory is the deepest theory we know, and that basically says that everything is a wave. And Edie showed us lots of properties of waves, all the basic features. So let's summarize those and then go into some more detail. So a wave is just an oscillation that travels through a medium. And if that medium is made of matter, for example, air or a rock or a guitar string, then we call that a mechanical wave. And most things that we've talked about thus far have been mechanical waves. The movement of a slinky, sound in air, the movement of the earth in an earthquake, the movement of a guitar string, those are all mechanical waves. Indeed, are there other kinds of waves? And the answer is yes. Sometimes the medium doesn't have to be matter. Sometimes, for example, it could be electric or magnetic fields, but we can talk about that more later. One thing that distinguishes a wave from other movement of matter is that the medium itself, on average, doesn't move. So when I talk to someone across the room, I'm not sending air across the room. I'm just simply sending wiggles in the air across the room. And in this way, we can transfer energy via waves. And so I give energy to the air just next to my vocal cords, and that gives energy to the air just next to it, and so forth. And so by making waves in the air, we can transport energy across the room without actually transporting the air across the room. We learned that we often distinguish between different waves depending on which direction the oscillations are. So if you have the oscillations in the direction of the motion of the wave, then that's called a longitudinal wave. And if they go sideways or transverse to the direction of the travel of the wave, then they're called transverse waves. Now in real waves, the shape of the oscillations in the wave can be very complicated, but we often follow a really simple model where that oscillation looks like a sinusoid, so a cosine or a sine. So this axis here will be distance, and this axis here, well, that depends on what kind of wave it is. So if this is an oscillation in, say, the voltage of something inside an electrical circuit, then that will be measured in volts. If that's the height of a guitar string, then that will be measured in meters. And so the units of the amplitude of the wave, remembering that the amplitude of the wave is how high it is between its medium point and the peak, so the units of the amplitude depends on what kind of wave it is. The wavelength is the distance between successive points on the cycle, so it could be peak to peak or trough to trough, and the wavelength is therefore obviously measured in meters. And because it's a wave, these oscillations are moving. So let's assume they're moving to the right, and so these peaks will be moving, the troughs will be moving, everything will be moving. And so if we just sit at one point, so if we just pick a point and sit there, then it's going to go down and up as this wave passes by. And so we're going to sort of be following this wave down just by sitting there. And so this point will come on down, and then when it gets to the bottom, when this bottom trough passes this point, then it'll be on the bottom. And when this top peak passes this point, then it'll have come right up to the top here. And so it'll also be going up and down in a sinusoidal motion. And the time it takes to go through one cycle is called one period. We often talk about how fast a wave is oscillating rather than how long it takes between each oscillation, and so we often use the word frequency, which is just defined as 1 on the period. So a wavelength would typically be in meters, a period would typically be in seconds, and a frequency would be in per second. And the SI unit for per second is called the hertz. So it's cycles per second. So once you understand these definitions, it's really easy to work out something like the speed of the wave. We know that a given point of the wave travels one wavelength in the period. And that means we know how far it's traveling and we know how long it takes, and therefore we get the speed just by dividing the distance by the time. So if we've got the speed of the wave is equal to the distance, the wavelength is usually written by lambda, divided by the period is usually written by capital T. And because 1 on the period is the frequency, you can also write that as the frequency times lambda. And so you get the speed formula not from memorization. Scientists prefer to understand things than to just memorize lists of equations. You understand that just because you know what the wavelength is and what the period is. Now, as we discussed before, having just one beautiful sine wave is a fairly artificial kind of situation. Even if I sing a really beautiful single note like la, If I were to look at that on an oscilloscope, I would see lots of different frequencies. I would see not just a sine wave, it'd be a little bit like a sine wave, but it'd have lots of little wiggles on it. And in fact, a real wave is typically lots of these things added together. So you have a particular sine wave added to another sine wave, added to another one, with different amplitudes and different frequencies and different wavelengths and different offsets. And all of that gives you a real wave. But these beautiful sine waves are interesting for some quite simple reasons. If we have very small oscillations in a very wide array of different media, then it turns out that a beautiful sine wave does in fact travel exactly like this at a constant velocity without changing its shape. So it turns out that understanding the properties of sine waves is a pretty good starting point for understanding the behavior of real waves. Going into the detailed reasons behind that is well beyond what we need to do now. Instead, we're going to go on and discuss some more important wave properties. But just for those who might like a very quick explanation as an extension, let's take a moment to discuss why so many different kinds of systems actually have the same mathematical description. So why one physical model works on so many different kinds of waves in so many different kinds of media. And the answer is, for all of them, the medium is trying to return to some basic state. For a guitar string, it's trying to be straight. For the surface of the earth, it's trying to be a nice still piece of rock. For the air in the room, it's trying to be an even pressure all the way through. And so when I induce a wave by stretching the guitar string or the rock or by compressing some of the air in the room, then the wave might be traveling, but if I look at one little piece of that medium, it's always being pushed back to where it started from. The air is always being pushed back to having a nice even pressure, the guitar string's being pulled straight, and the rock's being pulled straight. And so if we look at that little piece, it's got a force acting on it, pushing it back. And it doesn't matter what the shape of that force is. And that's the trick, you see. If I have a different curve for the force for each of those different situations, if I have just a small amplitude, if I have a little perturbation, then I'm zooming in on that curve. And if you zoom in on any curve enough, it looks straight. And so every different medium basically has the same kind of mathematics. It's just a linear force versus displacement. And that means that we get very similar models describing all the different kinds of waves.